Welcome to part 1 of the series Circles. And in this series, we're going to investigate circles and their various relationships with lines and segments. To begin with, it's important to begin with a few basic definitions. First, the definition of a circle. A circle is a set of all points in a plane that are equidistant from one point called a center. So this is the set of all points that have the same distance from that point, the center, as every other point on the circle. Second definition is the center. The center is a point that is equidistant from all points on the circle. And that brings up the idea of a radius. A radius is a segment from the center of the circle to any point on the circle. And that makes a very important relationship. As you can see, since this point is the same distance from that point as this point is, and as that point is, that tells us that all radii are going to be the same length, and therefore all radii are congruent. Now, this radius is a segment that has one endpoint on the circle and the other endpoint as the center of the circle. What happens when we have a segment that has both endpoints on the circle? This is called a chord. A chord is a segment whose endpoints are on the circle. This then leads us to a special kind of chord, which is called a diameter. A diameter is a chord that contains the center of the circle. And it's important to note that a diameter is the longest chord in a circle. Now, these are the fundamental objects we're going to be working with fairly extensively, but there are two more objects that we need to cover. The first is a secant. A secant is a line that intersects a circle at 2 points. This word gets its name from the Latin secare, which means to cut. So this is a line that cuts a circle at 2 points. The second one is called a tangent. And a tangent is a line that intersects a circle at exactly 1 point. And the point of intersection of the tangent and the circle is called the point of tangency. Now, a tangent gets its name from the Latin tangere, which means to touch. So a tangent touches the circle at 1 point. A secant cuts the circle at 2 points. And we're going to be using these quite extensively throughout this unit. Now let's take a look at how some of these objects interact. I'm going to start out this discussion by looking at circles that are in the same plane, or coplanar circles. The first group are called tangent circles, and they are coplanar circles that intersect at exactly 1 point. Here we have two circles intersecting outside each other, and here we have one circle inside another circle, also intersecting at 1 point. So those are coplanar circles. Then we have another group of circles. These are called concentric circles. Concentric circles are circles with a common center. And as you can tell, these are all different sized circles. And we're going to talk more about different sized circles a little bit later. But first, I want to take a look at the interaction between tangents and circles. And here we have three scenarios. First, we have a common tangent, which is a line rear segment that is tangent to two circles. So this line is tangent on the tops, on the bottoms, and these two circles, because they intersect, there's only two tangent lines that can be drawn with these two circles. Two common tangents, I should say. In this figure, these are two tangent circles, and therefore I can draw a line in between them in addition to the lines on top and bottom. And the reason I can do this is, of course, because a line is an object that has one dimension. It has no width. So its width is just 1 point, which has no dimension. Therefore, this can go in between both of them, and it actually touches at 1 point. And then the third situation is where the two circles are separated. In this case, I can have the two top and bottom tangents, but now I can also insert a tangent here and a tangent here. So you can have 4 tangents to this pair of circles. Along with this idea of tangents is the next idea, which is going to be our first theorem, which establishes a more formal relationship and a clearer definition of a tangent to a circle. This is the tangent line to a circle theorem, and it states that a line is tangent to a circle if and only if the line is perpendicular to a radius at its endpoint on the circle, which tells us this is a biconditional, and therefore if a line is perpendicular to a radius at that point, then the line is tangent to the circle at that point. And it also tells us that if a line is tangent to a circle, then it's perpendicular to the radius. We're going to use this very often in proofs and to solve problems that we ordinarily wouldn't be able to solve conveniently. And speaking of proofs, we come to the inevitable portion where we're going to prove this theorem. And I'm going to engage this proof in a rather unconventional way, so let's go ahead and get started with that. So here we're given circle C, and we're told that AC is a radius. We need to prove that line L is perpendicular to AC. Now this proof is going to be a little unconventional in that an indirect proof is what we're going to use. In an indirect proof, we first start out by assuming that what we're trying to prove is not true. We will fail in that proposition, thereby proving that it is true. So this is the conclusion we're trying to create. We're going to hypothesize that this is not true. So that's our first step in our proof. We assume AC is not perpendicular to line L. Now if AC is not perpendicular to line L, that implies that there must be some other segment that is perpendicular based on the perpendicular postulate. So there must be some other line segment perpendicular to line L, and we'll draw it in here. Now you can see that this line intersects the segment outside the circle. So in order for this to intersect this line, it must intersect outside the circle, and therefore this segment has to be longer than this segment. So if CD intersects outside, then the length of CD is longer than AC. So this segment is longer than that segment, which sets up a contradiction. Since the shortest distance from a point to a line is the length of a segment perpendicular to the line, and this segment is longer than this one can't be perpendicular. And so we have just shown that our original hypothesis has to be false. And this contradicts our original assumption that AC is not perpendicular to line L, and therefore AC must be perpendicular to line L. So indirect proofs are a little strange at first, but as you can see, they accomplish the task if done properly. The salient point to take away here is if you have a line tangent to a circle, then that line is perpendicular to a radius at that point of tangency. And if a radius is perpendicular to a line, then that line is a tangent to the circle. We're going to be using both of those extensively. Before we use this theorem in some problems, I would like to look at another theorem that uses the tangent line to a circle theorem in its proof. And those two theorems are very closely related. This theorem is called the external tangent congruence theorem, and it states two segments that are tangent to a circle at different points of tangency and share a common endpoint are both congruent. So BC and DC would be congruent because they share a common endpoint and are tangent to the circle at two different points. This gives us another definition, which is a tangent segment. DC and BC are both called tangent segments, and tangent segments are segments that have a point of tangency as one of their endpoints. So one of the endpoints of this segment is the point of tangency, and this endpoint of this segment is a point of tangency. Now let's go ahead and look at the proof of this theorem. Here we're given a circle, and BC and CD are tangent segments. We need to prove that segment BC is congruent to CD. The general strategy here is we're going to create some auxiliary segments in here, and we're going to create two triangles. One formed by this radius, one by this radius, and this segment from the center out to this point. And we're going to show that those two triangles are congruent, and therefore by CPCTC, these two segments are also congruent. So let's go ahead and draw some of these auxiliary lines in here and put it down our givens and move on from there. So here we have our given statements. We've drawn in our two radii and our segment from the center out to this common external point. Now out of the box, we know from our last theorem that AB is perpendicular to BC and AD is perpendicular to DC. And that's the tangent line to a circle theorem. So let's go ahead and write in that statement. So AB is perpendicular to BC, AD to DC. That tells us that angle ABC and ADC are right angles. So angle ABC and angle ADC are right angles. Definition of perpendicular lines. Now, to show that these two triangles are congruent, we're going to go for hypotenuse leg. So one of the legs is a radius. So AD is congruent to AB because all radii are congruent. We know that AC is congruent to itself by the reflexive property of segment congruence. And therefore, triangle DAC is congruent to triangle BAC. And that's because hypotenuse leg. And now that we know that these two triangles are congruent, we know that BC and DC are congruent by CPCTC. That was a fairly straightforward proof. Now let's go ahead and look at an example and put some of these theorems to use. In this problem, we're asked, is segment AB tangent to circle C? In order for AB to be tangent to circle C, based on the tangent line to a circle theorem, this BC must be perpendicular to AB. That has to be a right angle. Therefore, this has to be the hypotenuse of a right triangle. Therefore, these sides must match the Pythagorean theorem. And if you look closely, you can see that this is a 5, 12, 13 right triangle. So yes, in fact, this is a right triangle because this is a Pythagorean triple. And because of that, this is the longest side. The longest side is opposite the right angle. So this is the hypotenuse. That has to be a right angle. Therefore, this is perpendicular to that. And yes, then, AB is tangent to BC because AB is perpendicular to BC. So let's try that again just for clarity in case you didn't get it the first time. In order for this to be tangent to the circle, AB has to be perpendicular to BC. Therefore, this has to be a right angle. In order for that to be a right angle, this has to be a right triangle, and this has to be the hypotenuse. You can see that this is 5 times 2. This is 12 times 2. And this is 13 times 2. So it's a 5, 12, 13 right triangle, Pythagorean triple. This is the longest side, so it has to be the hypotenuse. Therefore, this has to be a right angle. If that's a right angle, this is perpendicular to this, and by the tangent line to the circle theorem, this has to be a tangent line to the circle. All right, well, we're going to work on another problem, but we're going to start it in the next part. So I'll talk to you then.